Hello everyone, good evening. So here we shall solve some more KCET previous year questions on the chapter chemical bonding and molecular structure. So any doubts if you have in any steps, then please write that in the comments section. We shall obviously clarify them in the subsequent videos. Also in any other chapter of chemistry, if you have more difficulty, then please write the name of that chapter also in the comments section, so that we can give more priority on it and solve more and more questions on that chapter. Also, some important homework questions on every chapter of chemistry will be uploaded in the Sapience Education application. So please install our Sapience Education application, whose link has been provided in the description. So here it is told the number of nodal planes present in the sigma star antibonding molecular orbital, sigma star antibonding molecular orbital. So sigma star s. Okay. So nodal plane, it means what? Nodal plane. Nodal plane, it means, so it is an image. So it is an a plane where the the probability density of finding the electron, or mod xi square, will be equal to 0. It means the probability of finding the electron, if it is 0 in some plane, then that plane will be called as the nodal plane. And how the antibonding molecular orbital is formed when two uh, two 1s pure atomic orbitals will overlap. When there is overlapping of two 1s atomic orbitals, so then two molecular orbitals will be formed. One is the bonding molecular orbital, which is the which will be called as sigma 1s, and one anti-bonding molecular orbital will be formed. One anti-bonding molecular orbital will be formed, which will be called as sigma star 1s. Now, bonding molecular orbital is formed due to the addition of these two wave functions. When these two wave functions will be added, means, let's say the wave function of this 1s or orbital is sigma a, is psi a, and for this one is psi b. So then the sigma, the psi for sigma bonding molecular or orbital is sigma a, is psi a plus psi b, and psi of sigma star will be equal to psi a minus psi b, and it's okay. So it means when there is destructive interference, when there is destructive interference of the two molecular, when the two um, when there is destructive interference of the two atomic orbitals, then an antibonding molecular orbital will be formed. And when there is constructive interference of the two atomic orbitals, then a bonding molecular orbital will be found. So it means the wave function of the sigma bonding molecular orbital will be formed when we add the two wave functions of the pure atomic orbitals, and the wave function of this sigma star will be formed when we subtract the two wave functions. So therefore, when the sigma star 1s will be formed, then these two molecular orbitals will be wave functions will be subtracted. So it means we will add the negative wave function will be added with the positive wave function of 1s. So then, like this, molecular orbital will be formed. Or simply I can say that two atomic orbitals will be subtracted. So then here plus and here minus, and here one nodal plane is formed. So here we will have one nodal plane only. One nodal plane only. So option C is the correct answer. Then it is told the overlapping of orbitals in benzene is of the form. Overlapping of the orbitals of benzene. So in benzene, the structure is like this. We have alternate single and double bonds, and it is attached with, and hydrogen is connected with every carbon atom, one hydrogen. So it is called the benzene ring. So here every carbon has got sp2 hybridization. Since why it is bonded with three surrounding atoms. It is bonded with three surrounding atoms. So it means that sp2 hybridization is the hybridization of every carbon atom here. So it is sp2 sp2. Okay, overlapping of orbitals of benzene. So it is sp2 is overlapping with sp2. Yeah, your sp2 is overlapping with sp2, and these sigma bonds are sp2 sp2 and s. So sp2 sp2 overlapping is there. So option A is the correct answer. And then the pi bonds. So here the carbon carbon sigma bonds which are formed, those are sp2 sp2 sigma bonds, and the carbon hydrogen sigma bonds which are formed, those are sp2s sigma bonds, and the carbon carbon pi bonds which are formed, those are pp p we can say 2p and 2p pi bonds. So pp pi bonds are being formed. So option D is also a correct answer. So A and D both are correct options. Then here the calculated bond order of superoxide ion is. So now we have to write the molecular electronic configuration, of the superoxide ion. So O2 minus ion, it has got 17 electrons. It has got 17 electrons. So therefore we have sigma 1s, then sigma star 1s, sigma 1s2, sigma star 1s2, and then sigma 2s2, sigma star 2s2, and then sigma 2pz2, and then we have pi 2px2 equals to pi 2py2. Then we have pi star 2px2 equals to pi star 2p1, 2py1. Okay. So here this uh, these all will get cancelled. Sigma star will cancel with sigma, sigma 2s will cancel with sigma star 2s, and sigma 2pz will not cancel. Sigma 2pz, this will not cancel. And pi 2px2 will cancel with pi 2px2, pi star 2px2. So therefore the bond order of the superoxide, that will be half of the number of the bonding electrons, that is number of bonding electrons, which is 4, and minus the number of anti-bonding electrons, which is 1. So that will be equal to 3 by 2, which is 1.5. So option A is the correct answer. So the bond order of this superoxide ion is 1.5. And here it is told among the following, the compound that contains ionic covalent and coordinate linkages. So we know that NH4Cl, NH4Cl, it has three covalent bonds with three hydrogens and one coordinate bond with one H plus ion, and then Cl with Cl minus ion, it is having an ionic bond also. Ionic bond is also there. Since by NH4 plus is NH4 plus and Cl minus, so here one ionic bond is also there. And then in NaCl we have Na plus and Cl minus ion, so here only there is ionic bond. And in calcium oxide also we have Ca2 plus ion and O2 minus ion, means oxide ion. So here also we have ionic bond only. And in NH3 we only have covalent bond and one lone pair on the nitrogen atom. So here only covalent. So in NH4Cl only we have ionic bond also and covalent bond also, and coordinate linkage also. So option A is the correct answer. Then here it is told a covalent molecule AB3 has a pyramidal structure. So its structure is like this. It is a pyramidal structure. The number of lone pair and bond pair electrons in the molecule are respectively. So AB3, so it is, so it has pyramidal structure. So it means that it should have one lone pair and it has three bond pairs, obviously. So the number of bond pairs is three, obviously. So the number of lone pairs is one. So it is AB3E type molecule. So AB3E type, it means, for example, we have NH3 molecule, NH3 molecule. So it is of that form only. So the shape is trigonal. Okay, the shape is triangular pyramidal. Triangular pyramidal structure it has. So the number of lone pairs is 1 and number of bond pairs is 3. So option C is the correct answer. 1, 3. Okay. Then it is told the correct statement with regard to H2 plus and H2 minus is. So for H2 plus it will have 1 electron, and H2 minus it will have 3 electrons. So according to the molecular orbital theory, the the molecular electronic configuration, the molecular electronic configuration of H2 plus, it will be sigma 1s 1. So therefore the bond order here, it will be half of 1, that is 0.5. And here also the molecular electronic configuration, that will be of molecular electronic configuration of H2 minus, that will be sigma 1s2 sigma star 1s1. So therefore here also the bond order will be half of 2 minus 1, means the number of bonding electrons minus the number of anti-bonding electrons. So that is also half, which is 0.5. So it means since their bond order is same, so they are uh, so they okay, their bond order is same, and since both have bond order greater than 0, so they can exist. So they can exist, but they can exist, but here uh, here since H2 plus has no antibonding electron, it has no antibonding electron, it means that it has no electron in the antibonding molecular or orbital, so it is more stable. And since in H2 minus it has has one antibonding electron. It means that it has one electron in the antibonding molecular orbital, so it is less stable than H2 plus. So H2 plus is more stable than H2 minus. So option C is the correct answer. Since why, if one electron is present in the antibonding molecular orbital, so it will have more energy. Since the rule is that antibonding molecular orbital, it has more energy. It has more energy, so hence we can have less stability. It has less stability than the bonding molecular orbital. Sigma star means the antibonding molecular orbital has more energy and hence less stability than the sigma bonding molecular orbital. So hence it means that H2 minus will be also less stable than H2 plus. Then it is told that arrange the following in the increasing order of their bond order. So O2 oxygen molecule, it will have 16 electrons. So if we write its molecular electronic configuration, then it will be sigma 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2 sigma star 2s2, then sigma 2pz 2, and then pi 2px 2 equals to pi 2py2, and then pi star 2px1 equals to pi star 2py1. So here these will cancel out, sigma 1s will cancel with sigma star 1s, sigma 2s will cancel with sigma star 2s, pi star 2. Okay, so therefore here the bond order of oxygen, that will be half of the number of uh, bonding electrons, which is 6, minus the number of antibonding electrons, which is 2. So that will be 4 by 2, that is 2. And now for O2 plus means it has 15 electrons. So it will be same as that of oxygen only. Only here we will have pi star 2p y 0. Pi star 2p. So I have to write till pi star 2p x 1. So it will be same as the electronic configuration of oxygen only, means it means that I will write from sigma 1s2 till pi star 2p x1, and this one pi star 2p y1 I will not write, since it has one electron less than that of oxygen. So here also the bond order of O2 plus, that will be obviously half of, here also it will come, so here also it will come sigma 2p z2 pi 2p x2. So the number of bonding electrons will be 6 and the number of anti-bonding electrons will be 1. So the bond order will be 2.5 here. Then for O2 minus, for O2 minus, there are 17 electrons. So here also it will be same as um, the uh, electronic configuration for O2 only. So here also it will start from sigma 1s2, then sigma star 1s2, then till it will go till sigma 2pz2, 2pz2, then pi star 2p, sorry, it will have pi 2px2 equals to pi 2py2, then then we will have pi star 2p x2 and pi equals to pi star 2p y1. So therefore here also the bond order of O2 minus, that will be equal to half of the number of antibonding electrons. These will get cancelled, and then the number of bonding electrons, which is 6, minus the number of antibonding electrons, which is 3, so it is 3 by 2, that is 1.5. Then the here at, actually I'm saying that the number of bonding electrons is 6, since why these I have cancelled it. If you w- want, you can also add these also, 2 plus 2 plus 6, so that will be 10, minus the number of antibonding electrons, it will be 2 plus 2 plus 2, that is also 6. So here also you will get the same answer only. So it means that if the like sigma 1s and sigma star 1s is there and they have the same number of electrons, then we can simply just cancel them. So here also, in case of O2 2 minus, it will have 18 electrons. So here also it will start from sigma 1s2, and then it will go to sigma, it will go till sigma 2pz2, and then pi 2px2, pi 2py2, then pi star 2px2 equals to pi star 2py2. So here also pi 2px and pi star 2px will get cancelled. Pi pi 2px, pi 2py2 and pi star 2py2 will get cancelled. So here all will cancel, only sigma 2pz2 will remain. So therefore the bond order of O2 2 minus ion, that will be also equal to half of 2 minus 0. So that is also 1. Or if you want, you may not cancel all these, and then you can add the total number of bonding electrons, which will be equal to 10, minus the total number of antibonding electrons, which will come 8. Then also you will get 1 only. So therefore here it is asked to arrange the following in the increasing order of their bond order. So the least bond order is for O2 2 minus, and then for O2 minus, the bond order is 1.5, and then slightly higher is for O2, and then the highest is for O2 plus. So for O2 plus has the highest bond order. So it means that option D is the correct answer. Then here it is told, which one of the following conversions involve change in both hybridization and shape? So in CH4, the shape is tetrahedral. It has tetrahedral shape, tetrahedral and tetrahedral shape, and the hybridization for carbon is sp3 hybridization. Since why it is connected with, it is bonded with 4 hydrogen atoms, and it has no lone pair also. And in C2H6 also we have 2 carbon atoms which are linked with 6 hydrogen atoms, and for each carbon we have sp3 hybridization, and so for each carbon atom the shape will also be tetrahedral shape. And then for, so it is for option A, and for option B we have NH3. So the shape of NH3 is, it is triangular pyramidal shape. It has got pyramidal shape, and the hybridization is sp3 only. And in case of NH4 plus, here also we have tetrahedral shape. Since this lone pair, it will be lone pair on the nitrogen atom, it will be shared with H plus ion. So here we will have a tetrahedral shape, and it will be, and nitrogen also will have sp3 hybridization here. So here the shape has changed, but the hybridization has not changed. And here in option A, the hybridization also has not changed and the shape also has not changed. So here we have to find in which of these hybridization also changes and shape also changes. Now BF3 is going to BF4 minus. So BF3 it has got uh, triangular, so or it can be called trigonal planar shape. It has trigonal planar shape, and it has no lone pair also. And so for BF3 we have sp2 hybridization, since why it is linked with 3 fluorine atoms. And for BF4 minus we have something called as back bonding. We have back bonding. It means that one fluorine atom, it forms a coordinate bond with the central atom, that is uh, boron. With boron it forms a coordinate bond. So here we have sp3 hybridization, and the shape also has changed to tetrahedral shape. So here in this case the shape also changes, and the hybridization of this central atom, that is boron, that also changes from sp2 to sp3 in option C. Okay, then in option D, H2O changes to H3O plus. So H2O, for H2O the structure is like this: two hydrogen atoms and two lone pairs on oxygen atoms. So here we have V shape, or bent shape, V shape or bent, and oxygen has got two lone pairs. So for oxygen we have sp3 hybridization. And then for H3O plus, so we have H2O and then one lone pair, it will form a coordinate bond with H plus. So here also the shape will be so three bonds and one lone pair, so it will be pyramidal shape. It will be triangular pyramidal shape it will be. And the hybridization also will be sp3. So here the hybridization is not changing, but the shape is changing. But in option C the shape also has changed, and the hybridization of the central atom has also changed. So option C is the correct answer. Then it is told the peroxide ion has 5 completely filled antibonding molecular orbitals. So peroxide ion is O2 2 minus ion, that is called peroxide ion. So O2 2 minus ion is somewhat like this. So here, mm, so O2 2 minus ion. So if we write its molecular electronic configuration, then we will have, that is sigma 1s2, sigma 2s2, no, sigma star 1s2, then sigma 2s2, sigma star 2s2, then sigma 2pz2, then pi 2px2 equals to pi 2py2, then pi star 2px1 equals to pi star 2py1. So here we have, since here we have 18 electrons, so here it will be pi star 2px2, pi star 2py2. Since y it will be 1 2 3 4 5 6 7 8 9 9 to 18. So here these two will get cancelled. Sigma 2s2 and sigma star 2s2 will cancel, and this will not cancel, and pi star 2px, pi 2px and pi star 2px will cancel, pi 2py and pi star 2py will cancel, since they have the same number of uh, electrons. So only pi 2px2 will, only sigma 2px z2 will remain. Therefore, the bond order will be half of 2, that is equal to 1. And mm, this one bond, it will be the sigma 2pz bond. And here it has no unpaired electrons, so it is diamagnetic. It is diamagnetic, diamagnetic. And O2 2 minus has got 18 electrons. So, and neon has got 10 electrons. So it is not isoelectronic with neon, but it is isoelectronic with fluorine. Since why any two molecule if I use, it will have 20 electrons. Any two means the neon molecule will have 20 electrons, so it is not isoelectronic with peroxide ion. But peroxide ion is isoelectronic with fluorine molecule, since it also will have 18 electrons, and it has bond order 1 also, and it has 5 completely filled antibonding molecular orbitals. Yeah, 5 complete. So the number of filled antibonding molecular orbitals are 1, 2, 3 and 4. So 4 antibonding molecular orbitals are completely filled. So here 4, so here 4 antibonding, 4 antibonding molecular orbitals are fully filled here. Okay. Okay. Which are sigma star 1s, sigma star 2s, and pi star 2px and pi star 2py. So it means the correct statements are the second one and the third one. Second and third are the correct, and first one has 5 completely filled. Okay. Okay. So it means here none of the options are correct, since why 2 and so here only 2 and 3 statements are correct. So in the option C, if we e- exclude the first statement 1, then only we can say that option C is correct. Else, actually here none of the options are correct. Then here it is told which one of these is not true for benzene. It forms only one type of monosubstituted product. Okay. There are 3 carbon-carbon single bonds and 3 carbon-carbon double bonds. Yeah, that is true. It has 3 carbon-carbon double bonds and 3 carbon-carbon single bonds. The heat of hydrogenation of benzene is less than its theoretical value. The heat of hydrogenation. So there are 3 carbon-carbon double bonds. Okay. So ac actually, due to resonance, due to resonance, the mm, due to resonance here, what happens? Each carbon-carbon bond length is the same. Each carbon-carbon bond length is the same, and so each carbon-carbon bond order also is will be the same. Each carbon-carbon bond order is also the same, and which will be equal to 1.5. It means that, so it is the one of the canonical structures of the resonance in benzene. So the actual re resonance hybrid structure, the resonance hybrid structure of benzene, that will be equal to like this. That will be, so each bond is the same. Each bond has the same order, which is 1.5. So all the pi electrons are delocalized among all the 6 bonds. So here all the 3 pi electrons, or the 3 pi bond electrons are delocalized among all the 6 bonds. So it means here we can't say that it has 3 carbon-carbon single bonds and 3 carbon-carbon double bonds. So here, since the bond order is 1.5, so here in benzene, what happens? In benzene, the bond length, the bond length of carbon-carbon bond is uh, is 1.39 angstrom. Is 1.39 angstrom, and actually the bond length of carbon-carbon double bond, for carbon-carbon double bond, the bond length is slightly lesser than this. So it is found to be 1.33 angstrom. And for carbon-carbon single bond, the bond length is 1.54 angstrom. So it means here we can see that when the we know that when the bond order increases, the bond length decreases. So here for single carbon-carbon bond, the bond order is 1. For carbon-carbon double bond, the bond order is 2. So here it is intermediate. The the bond length here, it is intermediate in between single bond and double bond. So here we can say that the bond order of carbon-carbon in benzene, that is less than, that is more than 1 but less than 2. So which is nearly about 1.5. So it means that option B is the correct answer, since why it is the wrong statement. And here in option C, it is told the heat of hydrogenation of benzene is less than the theoretical value. Yeah, that is true only, since it is also due to the resonance energy. Since why, as we know, resonance, the value of hydro, the experimental value of heat of hydrogenation, hydrogenation, that will be equal to the value, theoretical value of heat of hydrogenation, hydrogenation minus the resonance energy, minus the resonance energy. So the heat of exact value of the heat of hydrogenation of benzene is less than that of its theoretical value, since why there is a resonance in case of benzene, and since the resonance energy in benzene is having a significant value also, so the experimental value will be lesser than the theoretical value of hydrogenation. And the bond angle between the carbon carbon bonds is obviously 120 degrees only, since this bond angle will be 120 degree. So it means that option B is the correct answer, since it is the wrong statement. And in option A, it is told it forms only one type of monosubstituted product, which is also wrong, since why it can form uh, since the benzene ring can have two substituent also, or it can have three substituents also. So it can be disubstituted also, or it can be tri-substituted also. And mono substituted, it means that only one substituent is linked with the benzene ring, which is wrong, since why it can form various types of mono substituted products also. N- Not only one, various types of mono substituted products also, or it can form tri substituted and disubstituted products also. So then here it is told that when O2 is converted into O2 plus, then what will happen? So we know that the O2 has got 16 electrons. So its electronic configuration is sigma 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2 sigma 2pz2 pi star 2p x2 pi star 2p y2, then pi no sorry pi 2p x2 pi 2p y2, and then we have pi star 2p x1 equals to pi star 2p y1. Okay, so here the bond order of oxygen, that will be equal to half of the number of um, bonding electrons, which will be 2 plus 2 plus 2 plus 2 plus 2, which 1 2 3 4 5, which is 10 minus 8, which is the number of anti bonding electrons. So that will be, sorry, it is 6. The number of anti bonding electrons is 6. 1 2 3. So 3 is 6. So 4 by 2, that is equal to 2. And for O2 plus, and for O2, here we have a half filled molecular orbital. So it is having a paramagnetic character. It has paramagnetic character. And for O2 plus, it will have 15 electrons. And here I will go from sigma 1s2 to pi star 2p x1 only, since for pi star 2p y there will be no electron. So here the bond order of O2 plus ion, that will be equal to half of the number of bonding electrons, that will be also 10, minus the number of anti-bonding electrons, that will be 5. So it will be 5 by 2, that is 2.5. So, and here also we have one half filled molecular orbital. So here it will also have paramagnetic character. So hence the paramagnetic character So here it has got two half-filled molecular orbitals, and here it has only one half-filled. It has only one half-filled molecular orbital. So hence it means the paramagnetic character decreases and the bond order increases. Yeah, so it means option D is the correct answer. Since so therefore we can say that when O2, so O2 is changed into O2 plus, so then here the bond order is 2 and here the bond order is 2.5, but here the paramagnetic character, here it has two half-filled molecular orbitals and here it has one half-filled only, one half-filled molecular orbitals. So when O2 is changed to O2 plus, the bond order increases and the paramagnetic character paramagnetic character decreases. Decreases. So option D is the correct answer. So here it is told that the increasing order of carbon-carbon bond length for the following is, so in C2H4 it is ethene. C2H4 is called as ethene and the structure is carbon-carbon double bond is there. And four hydrogens are linked with it. And we have C2H2. C2H2 is called as ethine and its structure is it has got three, it has carbon-carbon triple bond. And C6H6 we have, that is the benzene ring. This is called C6H6. And C2H6 structure is C2H6 is the structure. So as we know that when the bond order increases, the bond length decreases. Now here the bond order is the highest in case of C2H2. So here the carbon-carbon bond length will be the least. So in C the bond length is the least. Then comes A, and then we have here we have like 1.5 bonds. The bond order is almost 1.5, since why here here the three double bonds are equally shared among all the six carbon-carbon bonds. So after A we have C, no, sorry, C2H2 is the B one. So the least one is B, A, then C, then we have D. So B, A, C, D. So option C is the correct answer. Then here, Then here it is told that which one of the following contains ionic, covalent, and coordinate bonds. So in NaOH, we have Na plus ion and OH minus ion. So here we have ionic bond, and in OH we have covalent bond. And in NaCl we have only ionic bond. And in NaCN we have Na plus ion and Cn minus ion. So in Cn also we have carbon, nitrogen, triple bond is there. And here also we have OH covalent bond there. And in NaNC, Na plus and Nc minus. In Nc minus we have uh, we have got coordinate bond here. So option D is the correct answer. Yeah. So here we have coordinate bond here. So here we have, so in NaNC we have coordinate bond also and covalent bond also and ionic bond also. So option D is the correct answer. Then here it is told which one of the following has no unpaired electrons. So in O2, the molecular electronic configuration for O2 we have one is sigma 1s2, sigma star 1s2, then sigma 2s2, sigma star 2s2, sigma 2pz2, then pi 2px2, pi 2py2, then pi star 2px1 equals to pi star 2py1. 2, 3, 4, 5, 6, 7. Since O2 has got 16 electrons, so here it has got it has got two unpaired electrons, so it means that in O2 minus it will have 17 electrons. So it will also have 17. So it will have one unpaired electron. It will have. Then in O2 plus will have 15 electrons. So here also it will have one unpaired electron. And but in O2 2 minus it will have 18 electrons. So there will be no unpaired electrons. There will be no unpaired electrons, since why here at the end we will have sigma star 2px2 equals to sigma star 2py2. So here there are no unpaired electrons. So option D is the correct answer. Which of the following is not a characteristic of a covalent compound? Which of the following is not a characteristic of a covalent compound, which is low melting point, no definite geometry, so insoluble in polar solvent, small difference in electronegativity between the combining atoms. So yeah, so here all A, C, and D are correct statements, but it has a definite geometry. We know that covalent compounds have definite geometry, and the shape of those compounds can be obtained using the VSEPR theory. VSEPR theory, which is the valence shell electron pair repulsion theory. So it has no definite geometry. That statement is wrong. So option B is the correct answer. Then it is told intramolecular hydrogen bonding is found in. Intra means that the hydrogen bonding is formed within the molecule itself. So in H2O and in NH3 we have intermolecular hydrogen bonding. Intermolecular hydrogen bonding. And in in salicyl aldehyde, which is also called 2-hydroxybenzaldehyde. 2-hydroxybenzaldehyde. So its structure is like this. So it is also called 2-hydroxy or orthohydroxybenzaldehyde. So here we have a hydrogen bond here. So here in salicyl aldehyde we have intramolecular hydrogen bonding. Intramolecular hydrogen bonding we have, since the hydrogen bonding is within the molecule itself. And in benzophenone okay, for benzophenone the structure is yeah, for benzophenone the structure is like this. So here we have no hydrogens, so hydrogen bonding is not there. But here these hydrogens will not form that strong hydrogen bonding here. So the hydrogen should be linked with the oxygen atom, then only there will be hydrogen bonding here. So in benzophenone there we have no hydrogen bonding. In benzophenone there is no hydrogen bonding. So in salicyl aldehyde only we have intramolecular hydrogen bonding. So option B is the correct answer. Now D2sp3 hybridization of the atomic orbitals gives. So D2sp3 means the steric number, is 2 plus 1, 3 plus 3, that is 6. So 2 plus 3 is 6. So the steric number is 6. So it means that it is AB6 type molecule. So for AB6 type molecule, we will have octahedral geometry. So we have octahedral geometry or octahedral structure. So option D is the correct answer. So hope all of you have understood the solutions of these questions based on the previous year KCET exam on the chapter chemical bonding and molecular structure. Still any doubts if you have, then please write that in the comments section. We shall obviously clarify them in the subsequent videos. Um, Also, please install our Sapience education application where we shall upload some important previous year KCET exam, which shall be obviously helpful for your exam. So thank you everyone. Bye.